All right, preparation for our final exam for Physics 252. So for exam one's material, we had Coulomb's law, Gauss's law, and transient circuits. I have these broken down by exam. So for Coulomb's law and Gauss's law, I did Coulomb's law here in red. We have the version that's force. And notice I did not show this as a vector equation. I showed it as a scalar. And since electric field is just force over charge, the only difference in these equations is, wrong charge, this capital Q does not exist in the electric field one. In this final form, I replaced K with 1 over 4 pi epsilon 0. Use either one depending on what makes you happy. So that's Coulomb's law. Then we have Gauss's law, which is, remember, this circle means it's over a closed, and since it's dA, it's over a closed surface. So the integral of E dot dA over closed surface is E, so that's what we call the electric flux, is equal to charge enclosed over epsilon 0. And that's the integral form. We have the differential form, which is the gradient dotted with the electric field is equal to the charge density over epsilon 0. So those are the two laws. Now, you need to be able to use them as you did in that first homework assignment. And if you're going to use them, you have to first know which one to use. So they're both fundamentally the same law. They're basically just different expressions of the same law. And so how you choose is based on exploitable symmetry. If you have an exploitable symmetry, i.e. spherical symmetry or cylindrical symmetry, or an infinite planar symmetry, then use Gauss's law, because it's almost for sure going to be easier. If you don't, then use Coulomb's law. Using Coulomb's law, it's describing the force between 2 point charges, but if you have a continuous distribution, that's why you have this dq and you have to integrate to add them all up. And so in your process, make sure you draw a figure. And if you have a one-dimensional, that is a linear charge distribution, then dq is lambda ds, where lambda is the charge per unit length. Lambda doesn't have to be a constant. If it's a two-dimensional distribution as charge is distributed over an area, then dq is mu dA. And once again, mu does not have to be constant. And if it's a three-dimensional charge distribution, of course, you can always do the three-dimensional. Then dq is rho dV, where rho is your, is your volumetric charge density. Use geometry to break into components. So in our homework problems, we had linear charge distribution, and then we broke it into components. So we broke into X and Z component, for instance. And then we solved each component independently. And then in the end, we just combine components like we've been doing since we started first semester. Now, if you're going to do Gauss's law, you want to identify a surface where the symmetry allows you to have either E dot dA is equal to 0, that is, electric field is perpendicular to dA, or E is constant on the surface and usually parallel to dA. So we usually shoot for one of those two. And that makes it really easy. I don't think we ever had to do an integral for the integral of E dot dA. Now, once you have that Gaussian surface, you also need to find how much charge is enclosed. So in some of our homework, you actually had a charge distribution, a charge density. And so the charge enclosed was equal to integral of rho dV over the volume that was enclosed. And so you do those two sides independently, and then you set them equal to each other. So here's setting them equal to each other. So you can then solve for whatever your unknown is, which is often the electric field. Now, the differential form, we did this with the one problem about the electric field in the atmosphere. And it's a very simple relationship between charge density and that gradient operator. Remember, the gradient operator in Cartesian coordinates is, I'll put I hat d dx plus j hat d dy plus k hat d dz. Partial derivatives. So if my if my electric field was x squared j hat plus x k hat, then my electric field only depends on x. Since it's a dot product, I'd be doing d dy of x squared. Well, x is a constant, that's 0. And then d dz of x, that's also 0. And so I would have had 0 for that case. Okay, last thing I think for exam 1 review is remember that the voltage difference is the change of potential energy over charge, but change of potential energy is minus work, so minus work over charge for the change in voltage. Work is integral of force dot dx, but force is QE, and so now the Q's cancel, and we're left with the change in voltage is minus the integral of E dot dx. And so we can calculate the voltage from the electric field, or if we take the gradient of both sides, it turns out that the electric field is minus the gradient of the voltage, right? Directional derivative is the inverse function of the integral of variable dot dx. So this is very useful. If we know the voltage function, we can always find the electric field. Now for exam 2 material, we had circuits here as well as magnetism. So starting with electromagnetism, Faraday's law of induction, the induced EMF is equal to minus n, number of loops, d flux dt. So the flux is equal to integral of b dot dA. And so you're taking the derivative of that with respect to time. No, since it's integral over space, I can move the derivative inside. And so anything, if B is changing with time, A is changing with time, or theta is changing with time, you're going to have an induced EMF. So you should be able to just go through and do a calculation. If you have this magnetic field, this dA, this angle between them, find what the induced EMF is. So that was Faraday's law of induction. That's the first one we talked about. I was thinking, I'm not done already. Now for transient circuit analysis, we have two fundamental relations for inductors and capacitors. For an inductor, the voltage across the inductor is the inductance times di dt. For capacitor, the current through the capacitor, and of course there's no current going through a capacitor, the current coming to it and the current leaving is C dV dt. Now, of a necessity, a derivative, unless I have an infinite voltage or an infinite current, this derivative has to be non-infinite, which means that in this case, VC is continuous. You can't have a discontinuous jump. And this one, IL, is continuous. Can't have a discontinuous jump. That's important for our initial boundary conditions. Well, you take these relations along with Ohm's law, and for your circuit, you either use Kirchhoff's voltage law or Kirchhoff's current law, whichever one makes you happy. You can do it both ways, to create a differential equation to describe the voltage or the current through the circuit. So you should have an equation that in the end only has voltage across, VL, or excuse me, yeah. It should only have a voltage and everything is dependent on that, or a current. And then you solve the differential equation. So that's another thing that you should be able to do. Now, Ampere's law, or Ampere's law, this is the one before Maxwell improved it, if you will, says that the circulation, the integral around a closed loop of B dot dL is equal to mu naught times the current that is passing through the loop, not the current in the loop, because it's an imaginary loop you're using for calculational purposes. Just like with Gauss's law, the surface you're using was an imaginary surface for calculational purposes. And so in this case, once again, you use symmetry, if you have it, to make it easy to calculate the circulation. And then you just determine pretty much by inspection what the current enclosed is. So you use Ampere's law if you have a symmetry that's going to make it easy. If you don't, then you've got the brute force Biot-Savart law. The Biot-Savart law, it's not the easy one. It's a vector equation with a cross product. But just like with Gauss's law, in the integral form, the best thing to do is to break this up into components. And notice the difference here is r hat over r squared, or r vector over r cubed. So they're the same. Break this up into components and then integrate each component separately. And of course, we did some examples of this. That's another thing you should be able to do. Now here's Maxwell's equations in their entirety. So we have Gauss's law, the electric form. Already talked about this. Charge enclosed is integral of rho dV, so that's why it has it that way. Differential form. Gauss's law for magnetism says that the magnetic flux on a closed surface is always zero, or the del dot B is zero. Faraday's law says that the changing magnetic field will induce an electric field. And Ampere's law says a changing electric field will induce a magnetic field. And so if we combine these as described with these four steps, then we can derive a wave equation. So, you can go back and look at the lectures when we went through that. Now, exam 3 material, looking at Snell's law, only two things, Snell's law and Fraunhofer diffraction. Snell's law, I think you said that you were actually ready for this one on the last test, and I went and asked something else. I think that was the case. Snell's law, it's a Brachistochrome problem here that we're going to do just to calculate and show that Fermat's principle, his principle is light takes the path of shortest time to go from point A to point B. So all you do is you say, okay, here's point A, here's point B, and here we define angle theta 1 and theta 2, and then you write an equation for the time that it takes light to go from A to B as a function of what this distance here is, x, and you get that equation for the total time, which I actually wrote here, v and v prime. V is the speed and the fast one, v prime the speed and slow one. And then you want to minimize it, so you take the derivative with respect to x and set it equal to 0. Right, that's how you minimize. And then you solve this baby, and it gives you Snell's law. So you should be able to go through and do that. Now, the Fraunhofer diffraction, this one was kind of complicated. The Fraunhofer diffraction with the double slit, that was not a big deal. But the single slit broke it up to an infinite number of little pieces, each one having a very small phase difference. And when you get to the screen, you add up all of those little phase vectors. And this last one here is at an angle which we can't see. That's this angle here. And then we use geometry to relate the difference between the starting and ending. So this is the electric field of the net result at the screen. And this here is the electric field that you would have had going through the original slit. And so your intensity is proportional to the electric field squared. And so you have intensity is equal to the initial intensity times, and you get the answer from relating the arc length here to that straight across. And so there's just some geometry. Go back and review how we did that. Exam 4. 4 vector addition and addition of velocities, and then radioactive decay. So once again, basically two things. So with the 4 vectors, our 4 vectors were x0 is speed of light multiplied by time, x1 is x, x2 is y, x3 is z. We always define the x direction such that the speed of the reference frame compared to the other reference, reference frame 1 compared to 2 is in the x direction. And so in doing so, then we worked out how we got these transformations, how the position in the prime reference frame relates to the position in time in the unprime frame. And likewise, or that was time, position relating to position in time, or the unprime frame relates to the prime. Now that was all fine and good. You really don't have to know how we got to this point, but you need to know how to go from that point to this point. So remember, ux prime is equal to du prime dt prime, where u prime, that's dx prime. U and u prime are the speed of the object in s prime frame. And if it didn't have the prime, it'd be an s. So u is dx dt. Well, we just use the relationship then that x prime is equal to gamma x1 minus beta x0. And so that means that dx prime dt prime is equal to d dt prime of and so we went through and we said that's equal to gamma times dx0 dt, dx0 minus beta dx1. And then for the dt prime, I used the x0. Oh, wait, I wrote that wrong. I was so ingenious of me. You have to use x1 is x, so that's x1 minus beta dx0. And then this is going to be and then all I did was I divided everything by dt. And in doing that, then we have dx1 dt is ux. dx0 dt is, since x0 ct is c, and then dx0 dt is again c, and boy, did I do that right? That's equal to ux minus v over c minus vux over c. And so if I seem to be off by a factor of c. I'm not sure where yes. I did, instead of dt prime, I did dx0 prime, but dt, t is x0 over c, so I should have had over c. And so that's equal to the right thing. So make sure you can do that. And then we had perpendicular. This was parallel. This is what we had in general physics class. You should also be able to do the addition of velocities if you have a motion perpendicular to the direction of the relative speed, so in the y direction or z direction. And the only difference there is you're going to use like this one on top. Now the decay constant, we had The decay constant is the probability of decay per collision times the number of collisions per time, which gives us the probability of decay per time. So our activity R is minus dN dt, where dN is the number of radioactive nuclei we have. And of course, dN dt then is the rate at which N is decreasing, which is why we have a minus sign here. And it's equal to the probability of decay per time multiplied by the number of nucleons. So taking that, I can take the right-hand side of this, and I have minus dN dt equals lambda n. Separate variables, minus dN over n equals dt. I'm going to, for convenience sake, multiply both sides by minus 1. And I forgot the lambda. And now we just integrate this bad boy. So if we integrate this bad boy, I'm going to have natural log of n over n initial is equal to minus lambda t minus t initial, which we just set t initial to 0. And if I solve that then for n, I get n equals n0 e to the minus lambda t. And so that is the number of nuclei I'll have remaining at time t. And then using this relationship that r equals lambda n, then r equals r0 e to minus lambda t. And so you should be able to get those equations from this starting condition. Now, that's it for our review. Now, for your final exam, you're actually going to have 2 calculus-based questions. One of them will actually, no, I take that back. You won't. I was confused. You only have one. You have exam 4 will have one that's over this last section, one of these 2 things, and then the final will have something over the entire semester. All right, I hope you feel prepared. Obviously, give me a call if you don't. Bye-bye.